Hey y'all, today we're going to be covering section 9.1 and 9.2. 9.1 is about stratospheric ozone depletion and 9.2 is about reducing ozone depletion. So the learning objectives that you're going to gain today are, first of all, how to explain the importance of stratospheric ozone to life on Earth. So we're going to learn a bit about stratospheric ozone and then how it is depleted through some human impacts and what this depleted ozone means for those of us who live on Earth. Then another learning objective is that you can describe chemicals used to substitute for chlorofluorocarbons, which are a molecule that you're going to learn more about, and how decreasing these will help to mitigate some of our ozone depletion. So first of all, we're just going to kind of talk about stratospheric ozone. Hopefully you remember from when we covered Unit 4 a while back. We have the stratospheric layer, which you can see here. It's above the troposphere. And this is the layer that absorbs a lot of our UVC and most of our UVB radiation. Now, UVC and UVB are really harmful to those of us on life because this is the wavelength of light that can actually destroy DNA. And so without this ozone layer blocking things, we would have never had life on Earth because we need this barrier to absorb all of those harmful radiation so that we are not having it damage our DNA. So the layer of ozone that we have in the stratosphere is very important to make sure that life is possible here on Earth. Now, some of the health benefits that we have is because we are not having our DNA totally destroyed by this, it's going to prevent skin cancer. It's also going to prevent cataracts, which already have damage to your eye. And because this UVB and C can mutate the DNA and cause oxidative stress in the eyes, this is what leads to that skin cancer and that cataracts. Now, we do have a small amount of UVB that does still get to the Earth's tropospheric level, and that's going to be the major cause of things like sunburns and skin cancer from sunburns. And so if we think that we only get like a small portion of it actually getting, and then how many of us have had sunburns, many of us probably know people who have had skin cancer. And so you think if that tiny amount can have that much of an impact, this is why it is very important that we do not have tons of it coming to us. Now, another thing to keep in mind, we're talking about the stratospheric level here. We have also talked about tropospheric ozone, which is what creates photochemical smog. So remember that when we have it in the troposphere, that's bad. That's how we get respiratory irritants. It damages plant tissue, and it's what's going to be ultimately leading to photochemical smog. When it's in the stratosphere, this is very good. We need it to make sure that our DNA does not get destroyed by this UV radiation. So how is it that ozone is going to absorb UVB and UVC? Like, what is the actual step-by-step process here? So first of all, we have oxygen, which is 2 oxygen atoms. The oxygen molecule exists in our atmosphere. And when we are having UVC radiation, when it comes and hits this ozone molecule, it's going to break it into 2 free separate oxygen atoms. Now, when we have these atoms just by themselves, what they're going to do, they're not very stable on their own. They're going to go and want to attach to another oxygen molecule in order to form ozone. And remember, ozone is 3 oxygen atoms. And so once we have those 3 oxygen atoms, that is our ozone. Now, this reaction we see going this way, but it can also go in the opposite way, where if we end up having radiation hitting ozone, then it's going to flip. It's going to cause one of the molecules to break off. We're going to end up with our oxygen gas and a free oxygen atom here, which when that is by itself, remember, it's not stable. It wants to bond with something. It's going to bond with the other free oxygen atoms, and then we are going to get more oxygen gas. And this is just going to be a continuing cycle where we have this formation and breaking down of ozone because of all this UVC and UVB that's coming in and kind of causing these molecules to break off and then reform. And this is ultimately still going to be allowing us to have a lot of ozone in order to protect all of us living here on Earth. So now what happens when humans get involved and we are causing some of this anthropogenic, which is human-caused ozone depletion, like the steps here. So we have these fun little chemicals right here that are CFCs, which stands for chlorofluorocarbons. And this is going to be the main thing that comes from humans that causes an ozone breakdown. So chlorofluorocarbons are like a really large grouping of chemicals, and they are used as refrigerant chemicals. They're used in, so anything that has coolant, like your refrigerator or ACs, stuff like that. And then we also have propellants and aerosol containers. So think of like your hairspray, your Axe body spray, things like that that have the aerosols. Those are going to be using the CFCs. So if you think of how many people you know that use hairspray or at some point in their life use something like Axe body spray, you can imagine how much of this ends up in the atmosphere. So what happens is when we have this CFC, UV radiation is going to hit it, and this is going to cause one of the chlorine atoms to separate off on its own. Now, a chlorine atom by itself is very unstable. It wants to bond with something. And because it is highly electronegative, it actually bonds to one of the oxygen in ozone and like pulls that oxygen atom off. So we end up having oxygen gas, and then we end up having this oxygen chlorine molecule here. Then what's going to happen is this is still not a very stable molecule. This oxygen wants to be better bonded to something else. And because we have an extra oxygen atom here from various reactions happening in the ozone, what's going to happen is this oxygen is going to pop off the chlorine, and it's going to go and find other oxygen atoms to bond to. Now, the problem with this is now all of our oxygens, that a lot of them should be in ozone, they're starting to get broken down into just oxygen gas, and we're getting less and less ozone. Now, this chlorine atom, remember, it's now off by itself. It wants to continue bonding with oxygen. Now that it's already destroyed one ozone molecule, it's going to go to the next one. It's going to bond like it did earlier. It's going to pull that one off, which leaves us with ozone, this oxygen, and this cycle is going to keep going to where we're having ozone broken down and we're just ending with oxygen gas. Now, one of the big concerns is the fact that this single chlorine atom can live in the atmosphere for 50 to 100 years, and it can destroy up to 100,000 ozone molecules in its life. So if you think of how much we have, that's a ton of ozone that's getting destroyed. And remember, when we lose the ozone, we lose that protection of the stratospheric ozone that is making it so that we don't have UV radiation ruining our DNA. Now, there is actually a natural ozone depletion, and it's important for y'all to understand the circumstances behind that, especially because sometimes people say, well, there's a hole in the ozone, but whatever, that's natural. So let me explain like what the natural ozone depletion is, because this does just naturally occur here on planet Earth. And this occurs basically only in Antarctica. So we end up having the spring melt, and what's going to happen is it's going to form polar stratospheric clouds, which look like this in the picture here. Now, these clouds are made of water and nitric acid, and this can only form in areas where we consistently have negative 80 degree Fahrenheit temperatures, which is basically only found in Antarctica. So this is the only place where we're going to be getting these polar stratospheric clouds forming that have this nitric acid. So now the process of how this happens. When we have these polar stratospheric clouds, we have the chlorine nitrate, which you see at this little molecule up here, and hydrochloric acid. They're going to react, and they are going to give off a 2 chlorine atom. So there, as a molecule, you'll get the chlorine molecule there. Now, this double chlorine molecule is going to get photolyzed, which is when it's broken apart by the sun. And then that's going to give us 2 free chlorine atoms. Hopefully y'all remember what chlorine atoms do to ozone. So even though this is a natural way, we still have the same issue with these chlorine atoms are going to go. They're going to start bonding onto our ozone. They're going to start ripping it apart. We're just going to have the oxygen. And then once again, we are depleting the ozone. But again, this is happening only in Antarctica because it is basically the only place where we're going to be getting that cold. So normally this was just going to be like a natural occurrence where it's like a thinning of the ozone. But because we as humans have released tons of chlorofluorocarbons, that plus this natural process leads to a lot of ozone depletion, which is why if you have heard of the hole in our ozone layer, this does occur in Antarctica. And Antarctica is the only place it's happening at this point because it's the only place where it's cold enough to also get that natural cloud formation. But these together are combining to result in this red part that you see here of like a hole in the ozone. Now, when we say a hole, it doesn't mean there is literally zero ozone there, because that would mean that any scientist who ever studies in Antarctica would get zapped into oblivion by the UV rays. When we say hole, we just mean it is like really, really, really thin, and it is not at the levels of ozone that we need. And so this is where you get that natural depletion combining with the human cause that come together to get us like pretty thin levels, nowhere near what we would like to have typically with our ozone. So now how is it that we can reduce this ozone depletion? Luckily, I do have some good news for you because I feel like right now this is all a downer. The main way to reduce this anthropogenic ozone depletion is by phasing out and replacing the chlorofluorocarbons, which in 1987, the world got together and passed this thing known as the Montreal Protocol. This was a global agreement to phase out CFCs out of production in refrigerators, aerosols, and other things. So we did this. And so at this point, we are not allowing these CFCs in order to be used. So instead, what we did is we replaced them with HCFCs, which is the CFCs just with a hydrogen added. Now, it's not super ideal. It is much better than what we had. However, these HCFCs do still deplete ozone, and they do act as a greenhouse gas, but to a much lesser degree than the CFCs. So if we're looking here at this diagram, CFCs is what we had, which the Montreal Protocol said no more. And then we have these HCFCs, which is where we have a low ozone depletion potential, is what that ODP means, but we still have a high global warming potential. So then we kind of want to be progressing our way through this because this is not a permanent solution. It does still cause problems with ozone, and it is a greenhouse gas. And so it's kind of a temporary solution. And so we're kind of in this transition phase. Now, the HCFCs need to be phased out of developing nations after 2020. So we're there. Developing nations do have until 2030. So these HCFCs are slowly getting phased out. And so the next one that we want to move to is the HFCs, which is the hydrofluorocarbons. These have zero of the ozone depleting potential, which is awesome, but they are still high in global warming potential. So eventually we're going to transition to the best of all of them, which is these HFOs, which stands for hydrofluoroolefins. And these have zero ozone depleting potential and very, very low greenhouse warming potential. And so this is going to be the best here. And so as we're kind of moving through this is the direction that we would like to go. And so, these last couple points here, just basically what I was just saying there, where CFCs, we don't use them anymore. HCFCs, we are phasing them out. And then this is the future of what we're moving to so that we get to the point where we don't have any ozone depleting molecules that we're releasing. And the ones that we're using are very low for our global warming potential, which is good all around. All right, so here's going to be your practice FAQs for covering 9.1 and 9.2. The suggested skill that you're going to get, you get 2 of them this time. It's going to be describing potential responses or approaches to environmental problems, and then also describing environmental concepts and processes. So for the first part here, I want you to describe how stratospheric ozone protects organisms on Earth from UV radiation. Then describe how these CFCs deplete stratospheric ozone. Then I also want you to explain how the Montreal Protocol decreased ozone depletion. And that's going to be your practice FRQ for 9.1 and 9.2. And those were your notes on 9.1 and 9.2 about ozone depletion and how to reduce it.